Okay, so this time we will talk about matrices as applied to combinatorics. So recall, combinatorics is really a study of counting or sort of discrete structures and so on. So what we want to do now is to talk about one such discrete structure, which is the notion of a graph. So this use of the word graph is different from the usual use of the word graph in the context of functions. This graph refers to the following pieces of information. There is a set of vertices which are connected by lines which we call edges. So vertices and edges. These together make up the notion of a graph. So let's just do it by example where it's clear. So when I say a vertex, so here's a graph which has 5 vertices. So let's call the 5 vertices as 1, 2. So they are labeled. Call this 2, 3, 4, and 5. So there are 5 vertices which are I think of as some 5 points in the plane, and what we have is between every pair I draw a line or I don't draw a line or I draw several lines and so on. So I think of for instance, say between 1 and 2 there is an edge. Okay, so you think of it as a path which allows you to go from 1 to 2. There is an edge between 2 and 3. Let's say there is an edge between 3 and 4, an edge between 4 and 1, and let's say an edge between 1 and 5. So this, for instance, would be an example of a graph where you have 5 vertices and certain edges which connects some vertices. So for instance, there is no edge between 1 and 3, there is no edge between 4 and 5, and so on, 2 and 5. These are all things which don't have edges. Now what we also allow is an edge which connects a vertex with itself. So this is sometimes called a loop. So you think of it as a path which starts and ends at the same point. And the other thing that you can allow is to have multiple edges. Say between 4 and 5, let's say there are 2 paths. Okay, so such a thing is sometimes called a multiple edge. Okay, so here's an example of a graph which also has loops and multiple edges. So we will pretty much allow this as the definition of graphs. Now how it is drawn is immaterial. Okay, this is just one pictorial representation of this graph. There may be many other ways. You can just move the vertices around, draw the edges any which way you want. All that matters is really which vertex is connected to which other vertex and by how many edges. Okay, so pretty much that's all that's pretty much what determines a graph. The drawing itself does not matter. Okay, so what's another way of saying it? Let's encode this graph, the basic data of this graph. So here's the encoding. We just keep track of how many edges there are between every pair of edges. Okay, so I will draw, I will write down a matrix. Let's call this matrix A. Okay, so this encoding is in the form of a matrix. In this case, it's a 5 cross 5 matrix. So the size of the matrix is just the number of vertices. And what are the entries of this matrix? So let's call it A. The I, jth entry of this matrix is just the number of edges between I and j. So vertex I and vertex j. So it's between I and j. So in this example, the matrix A for this graph would be the following. So think of, so let's just say, so I have, this is sort of this is the first row, here's the second row, third row, fourth row, and fifth row. And I also have first column, second column, third column, fourth column, and fifth column. And let's just write this down. Between vertex 1 and vertex 1, there are no paths because there is no loop there. In fact, that also tells us between 2 and 2, there are no vertices. There are no edges. Between 3 and 3, there is a loop, which means there is in fact one edge connecting 3 with 3. there are no edges connecting 4 with itself or 5 with itself. So you will only get entries along the diagonal when there are loops in the graph. Okay, so that's one thing to keep in mind. Now there is an edge connecting 1 and 2, 1 and 4, and 1 and 5. So between 1 and 2, 1 and 4, and 1 and 5. But there is no edge connecting 1 and 3. So the number of edges is 0. Now similarly, connecting 2 to 1 and 3, you have edges. So to 1 and 3, I have 1 edge each and 0 elsewhere. Okay. Similarly, connecting 3 to 2 and 4, I have 1 edge each. To itself, there is a loop. And from 4, I have to 1, 3. So from 4 to 1, there is a edge. 4 to 3, there is an edge. And 4 to 5, there are 2 edges. So it's a multiple edge there. So there are 2 paths between 4 and 5. Now similarly, between 5 and 1, there is an edge. Between 5 and 4, there are 2 edges. So that's the final graph that you get, the final matrix that you get corresponding to this graph. Okay. So this just encodes the number of paths or edges which connect each pair of vertices I and j, and observe that this is necessarily a symmetric matrix, meaning the I comma jth entry is the same as the j comma ith entry, because both of them are just the number of edges connecting I and j. Okay, whether you think of an edge as connecting I to j or connecting j to I, it is the same thing. So this is what's called a symmetric matrix. Things above the diagonal and entries below the diagonal are equal. This and this are equal, these two are equal, these two equal, these two equal, and so on. Okay, similarly, this one and that one are the same. Okay, so this is often called an adjacency matrix, the graph. Of the graph G that you started out with. Okay, so let's say of the graph. So adjacency just means it tells you how many edges connect two vertices. Okay, so now what we want to do, we want to see how this matrix allows us to perform certain kinds of counting on the graph, right? So we finally want to do combinatorics, we want to count things. So what's the natural thing that we might want to count? It's paths. So observe the edge. So I have, say, 2 vertices, 1 and so we had 1 and 2. Having an edge between 2 vertices is just, you can think of this as a path of length 1. Okay. Now you can extend that notion to, for instance, paths of length 2. So I can go from 1 to 3 by following a path of length 2, right? The thing which first goes to 2 and then goes to 3. Or I could say consider a path of length 3 as follows. I go down to 2, go to 3, and then follow the loop at 3. Okay, so here's a path which will get me from 1 to 3 in 3 steps. Okay, so the notion of a path itself is a rather intuitive and easy thing. Now what we want to do therefore is to count paths. Okay, so what we would like is to find the number of paths in a graph which connect any one vertex to any other vertex. So here's the problem question: find the number of paths in a graph which connect a vertex I to vertex j, let's say, which connect, okay, which have length. So the length of the path is also important, which have some given length, say length d, and which connect two given vertices and connecting vertex I. So there needs to be a starting vertex, so connecting vertex I to the vertex j. Okay, going from this vertex to the other vertex. Now how does one do this? How does one compute the number of paths? So in order to do this, let's sort of redraw the same graph that we had before, but with some decoration. So I'm going to draw the same graph, 4 connecting 5, say with multiple edges. But now in addition to having just the edges themselves, let's also label each of these edges so that you know which edge you take So let me call this as A. That's the edge label for the edge connecting 1 to 2. I have B, which connects say 1 and 4, C, which connects 3 and 4. D is the loop. Let's see. So I also have E, F, G, and H. So arbitrary labels. So there are 8 edges. So I'm just calling them, A through H in pretty much any order. It doesn't matter how I label them. Now here's what we'll do. Let's consider the adjacency matrix, but with this further decoration. Okay. So let's go back to our adjacency matrix, the same thing that we drew before. So it's right here. So here's the adjacency matrix, but let's also incorporate edge labels. Okay. So I'm going to just do it right here. So let me call this new matrix as A hat, the labeled adjacency matrix, if you wish. So the adjacency matrix with labels. So what is this going to be now? This A hat ij is not just going to count the total number of edges between the vertices I and j, but it will sum up the edge labels. So think of A hat ij as being the sum of the labels of the edges between I and j. Okay, so it's slightly more information, sum of the labels of edges between vertices I and j. Okay, what does that mean in this particular example? Let's do this. So I put a 1 here in the adjacency matrix because there is an edge connecting 1 with 2, but that edge is actually the edge with label A. So I should really call this guy as an A. Similarly, the thing connecting 1 and 4 is a B. It's a B. The thing connecting 1 and 5 now is an E. And so let's do this to all the other ones. So this is an A and H. And this is HDC. Now here's the interesting part. So this is B and C. Now observe there are 2 edges which connect vertices 4 and 5, and so what I'm supposed to do here is to write down the sum of the edge labels. So I should now call this entry as F plus G. Okay, and so now the rest of the entries are easy. So this is again F plus G, this is E, this is E, this is F plus G. Okay, so what we have now done is taken the adjacency matrix, but also now kept track of the labels. Okay, which edge is which? That's now clear from here. Okay, so now let's do the following. Let's think, for our purposes, let's think of A through G as sort of being like variables. Okay, so if you think of them as variables, then here's the relation between A hat and A, if you wish. So I had the matrix A to start with. What's the relation between A and A hat? Well, A is the following. It's just this labeled matrix A hat in which you substitute all the variables to be equal to 1. Okay, A hat with the following substitution: A, B, C, etc. all the way to H are given the value 1. Okay, so that's easy to see, right? If you just make them all 1, what you get back is of course the original matrix A, because now you don't keep track of the labels themselves, but you only want the total number. So you pretend each label is really just a number 1. Okay, and then what you will count is just the number of edges. So this is a relationship between the labeled and unlabeled adjacency matrices. But this labeled adjacency matrix has the following nice property. Okay, so let's compute the following. So let's calculate the square of this matrix. Okay, so let me call it something. I'll call it B hat, which is A hat squared. Okay, now what does square mean? Square just means it's A hat times A hat. I need to multiply the matrix with itself. Okay, now multiplying this matrix with itself of course means we need to go back to the definition of matrix multiplication. So recall that if I want to find B hat, say I want to find the ijth entry of B hat, this is just nothing but it's given by a summation, it's the following: k going from 1 to 5, a hat ik times a hat kj. So what is that? Of course, pictorially it's just you take the matrix A hat rather, and write down a hat next to it itself. Look at the ith. So this is the ith row of a hat, and you take varying entries in the ith row, and similarly you pair it up with the jth column of a hat and look at various entries there, and now you sort of pair entries in the ith row here with the jth column there and sort of multiply them out in pairs and add all the answers, right? So that's basically the same thing written out in this fashion. So for instance, what would this give you for certain special values of I and j? So let's compute in this so in this case, so let's go here, let's calculate a few entries. So if I compute b hat 1 3, okay, using this definition, here's what I'll find. So again, exercise to check that what I'm writing down is in fact correct. So this is just going to be AH plus BC. Okay, so just write down the definition of the product, and then you'll find that the 1, 3th element is just AH plus BC. Okay. Now here's something again that I should sort of emphasize. I said think of A, B, C and so on as being like variables. That's really why we are now thinking of you can add them or you can multiply them and so on. But I want to also keep in mind the following: the variables A through H are to be thought of as being non-commuting variables. So think of these as do not commute with each other. Okay, should be thought of as non-commuting variables. Okay, and that's sort of important. You'll see in a little while why. When we say non-commuting, we mean when you multiply A with H, that's to be thought of as being different from multiplying H with A. Okay, so AH is not the same thing as HA. Now, so we'll come back to this in a minute. When you do the multiplication, you need to keep this in mind all the time. Okay, the variables which occur to the left must be retained on the left. The variables which occur on the right must be retained on the right. Okay, you shouldn't change the orders. So now let's see what this means. So when I say b hat 1, 3 is AH plus BC. Okay, now the word AH, if you think of it as somehow encoding the path which first goes along A and then H, and BC as encoding the path which first goes along B and then along C, you will observe that AH and BC just refer to paths of length 2 which connect 1 with 3. Okay, so both of these guys here, AH and BC, are paths of length 2 which connect the vertex 1 with the vertex 3. Okay, so similarly, if you compute using the definition of the matrix product, if you compute b hat 1 5, here's what you will find. It's BF plus BG okay, and if you just see what BF and BG mean, B is this, F will be moving along the first of the two multiple edges, BG will still mean go along B but then follow G instead. Okay, so observe these are again paths of length 2 which connect the vertex 1 with the vertex 5. Okay, so b hat 1 5 is now, well, what is it? It really counts the sum of all edge labels or words which encode paths of length 2 between 1 and 5. Okay, so this is really should think of it as sum of, so let me say, so sum of paths, if you wish, or rather labels of paths of length 2 connecting vertex 1 to vertex 3, and similarly. Okay. So here's the interesting relationship, that if you compute b hat ij, what it really does is, so let's come back here, b hat ij is just b hat ij. So this is the fact, which again you should check at least by examples to convince yourself that this is really correct. B hat ij is just the sum of all paths of length 2 between I and j, sum of labels if you wish of paths of length 2 well, let's just say connecting I to j. Okay. Now, and it's not too hard to see why this really happens, because recall the definition of the matrix product set the following: it's A hat ik with A hat kj, and where k is supposed to run over all possibilities, over all possible vertices. So you should think of this as saying something like the following: I have the vertex I to start with. So here's the vertex I, and I have the vertex j. So I'm trying to get from the vertex I to the vertex j in 2 steps. So how could I possibly do that? Well, I need to have an intermediary vertex k. That's where I will jump after 1 step. So I first A hat ik will tell me how to go from I to k, which edge I should follow to go from I to k, and A hat kj tells me which edge I need to follow when going from k to j. Okay, and you sort of concatenate these 2 things together, that's the product, and you sum over all possibilities for this stopover vertex k. Okay. So it's kind of clear that this exactly does what we want it to do, which is it gives you all possible ways of going from I to j in 2 steps. Okay. And more or less repeating the same argument if you try, taking A hat power 3. So this is not a special thing just for 2. If you computed A hat power d, for instance, so let's just do this here. So here's a more general fact. If I take the labeled adjacency matrix A hat and I multiply it with itself d times, not necessarily 2 times, but I could do any number times, d times, and this is just A hat multiplied with A hat multiplied with A hat d times, and I try to find the ijth entry of this matrix. What I'll get is the sum of labels of all paths of length d which connect I and j. Okay. So I sort of urge you to play with this and see how this really works out in various examples of paths of length 3, for instance. Okay. Now, so here are a couple of things to keep in mind here, which is, as I said, if we don't really want, so the initial problem that we started out wanting to do is to find the total number of paths. We don't care about, suppose we don't care about knowing what the paths themselves are. So total number of paths of length d, let's say from I to j, if that's all you care for, well, then what would you do? You would do the following: you would first take all paths with labels. So you'd first take A hat power d, as I said, you take the ijth entry that will actually list out all the paths for you with labels, and then you just ignore the labels. Okay. In other words, wherever you find A, B, C and so on, you set them all equal to 1. Think of them as just being substituted as 1, okay, with all the variables assigned the value 1. But recall, when you do that, what you really are doing is replacing the matrix A hat with just the unlabeled adjacency matrix A. So another way of saying this is to say, well, forget the labels in the first place, consider just the unlabeled adjacency matrix, raise it to the power d, and then you take the ijth entry. Okay. So this is really the formula that this is the thing I mentioned in the beginning, an application of matrices to a counting problem involving graphs, which is to find the number of paths of length d. Okay. And the answer is this: you take this matrix, take the dth power of this matrix, and just take the ijth entry. Okay. So that's the very nice connection. The other point I want to make here is about the non-commuting nature of the non-commuting nature of the variables has the following consequence. So suppose I take a hat squared, the thing that we were trying to do, okay, and so this is what I called b hat, and if I compute the 1, 3th element, then what you would get, as we mentioned earlier, is AH plus BC. But if you now computed a hat squared but computed the 3 1th element, okay, not the 1 3th element, then here's what you will find. It will be HA plus CB. Okay, so please check both of these relations. The first one, again, is something we already saw, but here's the somewhat surprising thing. If you did in the other order, and since I'm sort of not allowing the variables to commute, the order is important. Here H will occur first, A next, C first, and B next. Okay, and this is not too hard to see why. So it seems as if this matrix is not symmetric anymore. Okay, if I do the square, cube, and so on, I will not get symmetric matrices because my variables do not commute with each other. But this is really how I would like to have them, because as we said earlier, the word AH refers to the path which first goes along A and then along H. So it's a path which connects 1 with 3, and BC is a path which sort of goes from 1 to 4 and then down to 3. Okay, so those are the two paths. But if I want to compute B hat 3 1 instead of B hat 1 3, then well, the answer I get is first H and then A, right? Which is really how I would like it to be, because it first tells me I need to go from 3 to 2 and then from 2 to 1. Similarly, I will get CB rather than BC, because C is the path which first starts from 3 and then following B is what will get me to 1. Okay, so I would in fact it's most appropriate for them not to be thought of as commuting variables, because only then it will correctly capture the actual labels of paths going from a given vertex to another vertex. Okay, so various, so there is really an interplay of several different things here. One, the fact that we construct a matrix and use sort of matrix operations, pretty much just matrix product, in order to capture this notion of paths. That's one. The other thing is somehow the use of these variables, the labels A, B, C, D, and their non-commuting nature to very accurately capture the actual path labels themselves, connecting any given vertex with any start vertex with an end vertex. Okay, so again I've left several things here for you to check. All of them are easy verifications, but it's something that you should certainly do yourself in order to get a very good understanding of what is going on here. Okay.